Hey Santino, how'd you ever come up with the resonance demo?
Well, actually, I was inspired by my great-grandfather, Santino Sr., who I heard all kinds of stories about growing up. He actually drove across the Tacoma Narrows Bridge.
You mean that suspension bridge that ripped itself apart?
Yep, that's the one. That's actually a classic example of harmonic resonance.
Woohoo! This is crazy! I've done the calculations and there's no way this bridge should still be standing. Some fool designed this bridge with a mechanical resonance point that is coincidentally excited by the wind, and there just isn't enough damping to keep it from failing. I have a feeling we'll be hearing about this in the Tacoma Times soon. I knew it! I knew it! Mamma mia!
You see, Tom, that story inspired me so much that I wanted to transfer that knowledge to other people. But because I'm an electrical engineer, I have to do that with the resonance demo to explain it to electrical people.
Makes sense to me.
Welcome to Eaton's Power Systems Experience Center. In this video, we will discuss this resonance demo and explain how we designed it to create resonant conditions to simulate what you might see on a real power system. Whenever you apply capacitors to a power system, you create two resonance points, series and parallel resonance. Sometimes we take advantage of series resonance by creating what we call a harmonic filter. Parallel resonance is usually unplanned and problematic. Harmonics are the new normal on power systems. Before harmonic producing nonlinear loads were prevalent, you could apply a capacitor on any power system without worry. But today, you have to consider series and parallel resonance, or, like the Tacoma Narrows Bridge example, bad things could happen. This demo allows us to create series and parallel resonant conditions for many scenarios, including series resonant with fifth harmonic filters tuned to 4.2nd, 4.7th, and 5.0, and seventh harmonic filters tuned to 6.8. We can also demonstrate filter combinations with fifth and seventh filters. Parallel resonance with a variety of capacitor sizes and 5 kVAR steps up to well over 200 kVAR, and parallel resonance with the seventh harmonic filter only when the fifth filters are off. We designed the interface to allow us to program various scenarios with an Eaton touchscreen PLC and SmartWire controls. Inside this demo, we also have two Eaton Power Expert meters with aux channels to monitor various points on the capacitors and filters, including the voltage between the capacitor and inductor on a filter, as the voltage rise on a capacitor is often a concern that we can demonstrate. We also use this Eaton Power Factor controller to mimic what would be done with an Autovar cap bank that automatically switches in and out steps or stages of capacitors or filters. The Power Quality Lab here at the PSEC is the perfect location for this resonance demo. All of the scenarios can be done with a significant amount of harmonic current generated by 6-pulse drives, as well as linear load from our customized load bank. In addition, we can show the effect of changing from a normal utility source to a high impedance generator source. Just so you know, this demo unit is very unique and you won't see anything like it in the world. It started out as an Eaton Autovar 600, but as you can see, we redesigned it with many additional components and safety features to illustrate some really cool and complicated resonance situations. I guess what I'm saying is, please don't try this at home. Let's back up a second and define resonance. Series resonance occurs when you put a capacitor in series with an inductor. We call this a harmonic filter. We tune this filter to a specific frequency by selecting the components that match impedance at the desired tuning frequency. Since the impedance of an inductor is defined by 2 pi times frequency times the inductance, its impedance increases as the frequency increases. The impedance of a capacitor is the opposite. It decreases as the frequency increases because its impedance is 1 over 2 pi times the frequency times the capacitance. When the two impedances match, the filter is a very low impedance, almost a short circuit, aside from a little bit of resistance. Harmonic current of that frequency flowing on the power system at that voltage level will want to go through that filter path. The current simply divides, as all current does, to the path of least impedance, so the closer you tune a filter to the frequency you want, the more effective it is. Using software like SKM, you can model the filter components and determine the ratings so that you can first remove as much harmonic current as you want from the system. Second, prevent overload of the inductor or capacitor components. And third, provide a power factor correction with the capacitor at 60 Hertz. When you tune a filter, you typically tune it below the frequency of interest. Say, for example, the fifth harmonic. Often, we tune a fifth harmonic filter to the 4.7th to capture maybe half of the fifth harmonic on the system, or even the 4.2nd if we are less interested in filtering harmonics, but more interested in providing reactive power or power factor compensation. When we purposely place these components in a circuit, we call this a harmonic filter. When this occurs accidentally, for example, when a transformer and capacitor are in series, from the point of view of a harmonic source, we might call this an accidental filter because you could draw harmonic current into the capacitor from other harmonic loads on the power system. When this occurs, you may overload the capacitor and often blow fuses or trip the breaker feeding the capacitor, so you should take care to understand what might happen anytime you apply capacitance. So here we have the resonance demo. Up top, we have HMIs, and these are displaying all of our metering information. Here is the switch that turns the system on. It also switches between automatic controls that exist in the Autovar 600 and the PLC that we have programmed to do the different types of filtering. For the first type of filtering, let's talk about series resonance. So this is the home screen for the Resonance Demo PLC. Here we have an example of harmonic resonance as our background. We have our power button, and this is just going to engage our logic, and then we have our two choices: series resonant for harmonic filtering and parallel resonance for harmonic enhancing. And I'm going to choose series resonance. We're going to notice now there's a discharge on all of the stages. This is making sure that any capacitors that are charged will fully discharge before switching them back onto the bus for safety. Each filter has two stages. For example, if we wanted to turn on the 4.2nd harmonic to do power factor correction, I could turn on stage 1. If I need more power factor correction capacity, I can hit the button for both stages. Now, upon switching from the 4.2nd harmonic to the 4.7th or the 5th, in order to do harmonic filtering, we're going to notice that stage 1 and 2 of the 4.2nd are going to have a cooldown timer. This allows the elimination of any DC trap charge on the capacitors dealing with those stages. This is important because the capacitors could be charged to, say, the negative voltage peak of the system, and if you switch them back in too fast, the system could be at the positive voltage peak, and for a 480 volt line-to-line RMS system, this could be upwards of a 1400 volt potential difference, damaging the capacitors. There is also a reset button that will reset all of the stages and cool them all down to ensure that all capacitors are discharged. If you ever want to filter more harmonics than, say, just the 5th, we call this a multi-stage filter. For the example here, we're going to switch in the 5th harmonic before the 7th harmonic. You would never want to switch in the 7th harmonic by itself. So if I come here and I hit stage 1 of the 6.8th harmonic, one of the 5th harmonic stages is going to switch in first and charge up. So here we have the 4.2nd harmonic stage 1 switched in, it's charging for a few seconds, and now we have stage 1 of the 6.8. Now, let's talk about parallel resonance. Parallel resonance is usually much more destructive and problematic. Parallel resonance occurs when an inductive component is in parallel with a capacitive component on a power system from the perspective of a harmonic source. The typical situation that causes parallel resonance is simply applying power factor correction capacitors on a system where the main transformer and the capacitor are in parallel from the point of view of variable frequency drives or other harmonic producing loads. By knowing the signature harmonic from various loads, like 6-pulse drives, we can estimate where resonance may be a problem. This example shows the parallel resonant point and how easily you can estimate the frequency at which parallel resonance occurs. For this example, parallel resonance occurs at the 7th harmonic order, and therefore any 7th harmonic current created by the drive will be amplified by the resonant circuit between the capacitor and transformer. Tens or even hundreds of times more current will flow in the resonant circuit than was produced by the drive until something fails. This is why we unfortunately call parallel resonance a self-correcting problem. Something will eventually fail, taking the system out of resonance, just like the Tacoma Narrows Bridge. When stepped or multi-stage power factor capacitors are used, many parallel resonant points occur, and generally you will find that one or more of the stages will be problematic and will resonate with harmonics generated on the system. So now we're back at the home screen, and again I'm going to enable the logic. To get to parallel resonance, I'll simply hit this button, and now we'll get to the parallel resonance screen. we're going to see now that all of my kVAR steps are covered with what's called an initial cooldown timer for all the capacitors. This is very similar to what we saw in the series section, where every capacitor needs to cool down for at least 45 seconds to dissipate any trapped charge. Okay, so now that our cooldown timer is gone, we can switch in steps as small as 5 kVAR. And we're going to see we have a meter here on the left that is reading 5 kVAR, so this is simply letting us know how much we can switch in. And the limit that we set for safety is 200. So if I try to switch in anything over 200, so now I'm at 155. So if I try to hit it another 50 and put it at 205, I'm going to get a warning. And this warning is going to tell me I attempted to switch in over 200 kVAR, so it's not going to allow me to do this. So I'm just going to reset that warning, and we're going to put all the buttons back into place. That 50 did not switch in. So if I want to enable that 50, I can switch out this 50 and enable that 50. So again, we're back at 155 kVAR, and notice that this 50 kVAR is actually grayed out. So this kVAR being grayed out is just another cooldown timer to allow that particular set of capacitors to dissipate any trapped charge. There is also a reset all button, and this will gray out all of my steps that were in use and ensure that their charges are dissipated. Power system modeling programs like SKM can help you visualize effects of resonant circuits and the amplification factor. This SKM curve shows frequency scan for our demo system, illustrating the points at which various stages of capacitors will create problematic conditions. Avoiding parallel resonance can be done by changing the size of the capacitor, but then you may have other issues with power factor penalties. You can assume that any capacitor will always increase your harmonic current on the system. The question is, how close are you to resonance and how much will harmonic currents increase? Another important thing to consider is the parallel resonant point of harmonic filters, which in general is 1 or 2 harmonic orders less than the tuning point. So for a 5th harmonic filter, that would be around the 3rd or 4th, where very little harmonic current exists. But for a 7th harmonic filter, the parallel resonant point is just above the 5th harmonic. This illustrates a specific problem that people encounter with multi-stage filters where the tuning point must be at the lowest expected harmonic. Usually 5th harmonic for 3-phase loads and 3rd harmonic for single-phase loads. To convey that point, I'll show you what we can do on the demo unit using the 7th harmonic filter without the 5th harmonic filter. Remember when I talked about the fact that we never want to turn on the 7th harmonic by itself? Well, here we actually put in a button where we could have an override and turn on the 7th harmonic by itself. But we do have a safety where it'll turn off after 5 seconds. So here I'm going to turn on the stage 1 override. So now the 7th harmonic filter's on. Right now we are filtering 7th harmonic current, but we're actually enhancing the 5th harmonic. And now you can see the 5 seconds is up, and all of the capacitors are going to make sure that they are discharged. Before harmonic loads were prevalent on power systems, you could place a capacitor anywhere on a system without worry. Even though a resonant point was created with that capacitor, there was no harmonic current to amplify, just like if the wind didn't blow to make the bridge oscillate. If there is nothing to excite resonance, you don't have to be concerned. Today, with the amount of harmonic current on our power systems, we have to consider harmonic resonance if we are applying power factor correction capacitors or harmonic filters. This demonstration can help you understand what you should consider regarding resonance. This demo not only allows you to see how harmonic filters work, but can help you with applying power factor correction capacitors to make sure they won't be damaged by resonance. If you want to learn more about harmonics and see this really innovative way to show harmonic resonance, contact us or your local Eaton representative to schedule a visit to the Power Systems Experience Center today.